podcast is brought to you by LMU Munich.
A few also from my side. So my name is Johanna Erdmenger. So let me write this down. So, and I'm going to tell you about GaugeGravity Duality. And so I'm based here at the Max Planck Institute for Physics here in Munich. And also I'd like to introduce the 5 tutors who are going to do the exercise classes this afternoon for this course. And so these will be Andy O'Bannon, Shu Lin, and Hai Ngo, Viviane Gras, and Martin Ammann. So these are the tutors, and so they prepared some really nice examples for you, and so I really encourage you to go there and to learn about these things in much more depth than I can tell you here on the blackboard. And the most important thing is that the sheet where you can find the examples for these questions, they will be handed out outside this lecture hall when you leave for lunch. So I know you have a very busy schedule, but maybe before you go eating, you can pick up one of these sheets and already read the questions before actually the class starts. And that would be really good. So don't forget to pick up examples sheet before you leave outside, okay, outside this hall, before you leave for lunch. And read it before you come back, okay. Okay, so I'm going to introduce you to this very fascinating topic of GaugeGravity duality. And I thought as an introduction, I'll present a few general remarks, a loose collection of remarks to give you a kind of overview, because as you will notice, it's a rather complex subject in the sense that it gathers very different areas of theoretical physics and provides new links between them. And this makes it difficult to explain what really the essence is, but at the same time it makes it a really fascinating topic, because things you never dreamt of have anything to do with each other are actually the same. And that's why this topic is so exciting. And so let me begin by giving you a selection of general remarks about this. Okay, now I have to, I meant to understand how this works. Okay, so I'll start with an introduction. And so the topic of this introduction is, so what is GaugeGravity duality? And I'll try to give some short answers to give you a flavor of this. Okay, so the most general statement which we can actually make to understand what this is to say that some quantum field theories, and I'll be more precise about some in the course of the lecture, they are actually equivalent to particular quantum gravity theories. And I put this quantum in a bracket for a reason which I'm going to explain next. Okay, so it's really some quite astonishing relation that you can actually map particular quantum field theories with the emphasis on quantum. So like the theories you have to describe the standard model of elementary particle physics, although well, that particular example in full won't work, but theories which have this structure and are similar to the ones of the standard model. And we can actually map these quantum field theories in flat space to particular gravity theories and even quantum gravity theories. But the reason I put this quantum in brackets is because we're going to consider a particular limit of this relation. So we are not going to consider it in full generality, because this is such a general statement, it will be really hard to actually prove it. But so one particular feature which I want to explain to you in the course of these lectures is that we take particular limits in which we can understand this relation. And in particular, we're going to consider a limit where this gravity theory which is involved here becomes classical. Sorry, the gravity theory. I hope you can read this. So the gravity theory becomes classical. Okay, and the same limit, if on this side we have the correspondence here between the quantum field theory and the gravity theory, and if we take the same limit, this gravity theory which we have on this side of the board will become classical, but at the same time this theory will become strongly coupled. Okay? So the gravity theory becomes classical, and the quantum field theory, so QFT stands for quantum field theory, becomes strongly coupled. Okay, so we will consider a particular limit where we can map a strongly coupled quantum field theory to a classical gravity theory. Now, of course, this relation which I have told you about here is very exciting for many conceptual purposes, because you can really say something new about quantum, and you can say something new about gravity and the relation between them. But if we take this particular limit, of course, as you can see, we consider a special case. But this special case is very, very useful, because we can consider quantum field theories which are strongly coupled, and usually, so as you probably know, in quantum field theory, to actually calculate something, normally people use perturbation theory. But if you do perturbation theory, you make a Taylor expansion in the coupling, and that you can only do if the coupling is small. So if you have a strongly coupled quantum field theory, then you can't use perturbation theory. However, there are many important examples in nature where you actually want to study strongly coupled quantum field theories. And now I have told you about a new possibility to study these strongly coupled quantum field theories, because now with this particular equivalence, you can map them to a classical gravity theory. Okay, so you can take this complicated, strongly coupled quantum field theory and you map it to a classical gravity theory, and there usually it's not so difficult to do a calculation. And so this provides a new approach to actually do calculations for interesting physical systems which you can't treat in any other approach. Okay, so at the same time as being conceptually very exciting, this correspondence is actually also very useful. And this I also want to explain in this lecture. Okay. Okay, so I continue with my selection of remarks about this. So one further important note, of course, is that this correspondence actually originates from string theory, and that's why I'm talking about this in the context of this particular course. And I especially put some emphasis on how you can actually derive this correspondence, or how you can establish this correspondence within string theory. okay, maybe at this point already I should state that this amazing relation, till the present day, there is no mathematically watertight proof of this, but nevertheless, there are lots of very good physical arguments why this should work. And okay, so one should always be aware of this fact that there's not yet a proof of this equivalence, but I show you many, many examples where it's just physically extremely plausible that this should work. But nevertheless, bear in mind that there is no proof so far. Okay, now let me make a little technical remark about this limit, just to point out that this correspondence doesn't work for any quantum field theory. I mean, that would be fantastic, but unfortunately, we're not that far yet. So further, let's make a further remark about the limit. And in fact, this limit is a so-called saddle point approximation. I'm not going to explain today what this is, just it's a technical term for a particular approximation. I'll talk about this more on the second lecture on Thursday, but let me point this out right now. So the limit, which takes the quantum gravity theory to the classical gravity theory. So this is a saddle point approximation. Okay, and if we have an equivalence and we take limit on the one hand side, we should also take it on the other side. And so this brings me to the point that I have to mention that the theories involved on the quantum field theory side are usually SUN gauge theories. Okay, another technical term. Let me just write it down for now. But for this gauge theory, we actually have to take the same limit, the same approximation. And what it does is the following. So on the field theory side, so we have an SUN gauge theory okay, if you know what this is, then that's perfect. If you don't know, then don't worry, because we're not going to need it today, and next time I'll say some more about this. And so in this particular case, the same approximation, so the saddle point approximation, corresponds to taking the limit that the rank of the gauge group, so this n of SUN, should go to infinity. And as I probably won't have time to explain, but I just want to mention it once right at the beginning, such that you bear this in mind. If you take this limit in the quantum field theory, then it means your Feynman diagrams become a lot easier than they would normally be. And in fact, in this limit, only the so-called planar Feynman diagrams contribute. Okay, the message you should take away from the sentence I'm just saying is, we look at a particular quantum field theory and we take a particular limit. And so that's quite a restriction on the quantum field theories you can actually consider in this context. So in this limit, only the so-called planar Feynman diagrams contribute. Okay, so this was a slightly technical remark, but I thought I should say this once at least in the series of lectures. And now, so let me be even more precise about this duality we are considering. Okay. Okay, so that wasn't so good. Sorry. Okay. So next remark. So next point is, so this gauge-gravity duality, this relation between gauge theories and gravity theories, actually is a generalization of a duality which was found earlier, about 13 years ago now, by the Argentinian physicist Juan Maldacena, and this duality is named the ADS-CFT correspondence. So that's my next remark. So gauge-gravity duality generalizes the so-called ADS-CFT correspondence. Okay, and so if I want to explain to you what gauge-gravity duality is, I should take this best understood example, which is the ADS-CFT correspondence, and explain to you what it actually means. And so first let me introduce the abbreviations. So ADS stands for the so-called anti-de Sitter spacetime. So de Sitter was a Dutch relativist, was a good friend of Einstein, and anti-de Sitter means that some particular sign is being turned around in the metric. And so this will be our example for our curved space, which enters the gravity theory in this correspondence. And later today, I will spend some time to explain what this ADS space actually looks like. And on the other hand, CFT stands for conformal field theory. And this is a particular quantum field theory which has a particularly high degree of symmetry. And also today I'm going to show you what the properties of such a conformal field theory are. Okay, but by using this terminology, I can now actually state slightly more precisely this gauge-gravity duality in this example where an anti-de Sitter space and a conformal field theory are involved. And that's what I'm going to do now. So, as I already mentioned so far, the ADS-CFT correspondence is a conjecture, but one which is very well motivated physically and has passed many tests. So, the conjecture, which is actually due to Maldacena from 1997, and what he said more precisely was that there is an equivalence between one, so corresponding to the left-hand side of what I introduced for the gauge-gravity duality, a four-dimensional quantum field theory with conformal symmetry. So a rather special quantum field theory. And just to give you an example of the one which was considered by Maldacena, so you don't have to understand all the words I'm going to say now. I just want to say you can actually write a Lagrangian for this quantum field theory, like you always do in quantum field theory. And there's a certain well-defined field content of this theory. And just for completeness, let me write down its name. So we could consider the so-called supersymmetric SUN Young-Mills theory. Okay, so SUSY stands for supersymmetric. Okay, and secondly, you have a superstring theory. So the quantum gravity theory, as mentioning at the beginning, is actually a superstring theory. On a particular 10-dimensional curved background, and this background involves anti-de Sitter space. Space-time, I should say. Okay, so that was his conjecture that actually these theories are equivalent. And so what does it now really mean to say it's equivalent? So on one hand side, I have this quantum field theory, and here I have a superstring theory on a particular 10-dimensional background. And the conjecture, in fact, states that these two theories are equivalent, including all the observer lists, the states, and lots of other physical properties. And so the correlation functions and the dynamics should also be the same. So the conjecture states that these two theories are equivalent. And so this means that the observer states and the physics should be the same. So the observables, the states, the correlation functions, and the dynamics. Okay, so I have written this conjecture for you here, and you should be quite impressed that these two theories, which actually seem to be so different from each other, are actually equivalent. And so the purpose of today's and Thursday's lecture will be to motivate further why this can be true. Yeah? Yeah, this I want to explain, so you're jumping ahead a little bit, so I want to give you the full details of how this will work. And so
one more question. And in which sense, for a four-dimensional theory is conformal theory? For example, a two-dimensional theory, a two-dimensional conformal theory has something like a Virasol algebra, and the property of the theory is defined with this algebra. And
yes.
What is the analog of Virasol algebra in this theory?
Okay, it's an excellent question. I will take the next half an hour to answer it, and then maybe in half an hour you can ask again, because this is exactly what I want to explain now. Okay, very good question. So you're really paying attention very well. So I want to explain to you what this equivalence means. But if you want to understand what the equivalence means, then of course we first have to understand what the ingredients are. Okay. So if I tell you a conformal field theory is equivalent to a gravity theory on ADS space, then first I have to explain what a conformal field theory is, and I have to explain what ADS space is, and then we can understand what the relation is. And so today, I'm going to explain to you now two important ingredients in this correspondence. First of all, I'm going to explain to you what is a conformal field theory in 4 dimensions. And also, I'm going to explain to you what is an anti-de Sitter spacetime. Okay, I guess you agree with me that if you want to understand what the relation between these two things is, we need to know what this is and what that is. And that's why I'm going to explain to you now. And I think this will be exactly what you asked. And okay, so first I'm going to explain the conformal symmetry. And okay, your first question was what exactly is the dictionary? And again, I mean, I'm going to explain this in more detail on Thursday, but just since you're asking, let me explain that here we will take some particular operators here in this quantum field theory, and we will map them to particular fields in this gravity theory. And the dictionary by which we can actually map the two is the symmetry properties. So that's why this example is so good, because there are so many symmetries that you can identify the representations of the two sides, and then you get a precise one-to-one dictionary. Okay, but that was the answer to your question, but okay, this was jumping a little ahead to the lecture on Thursday, and then I explain this in much more detail. Okay, so this brings me to the purpose of these lectures. Oops. So what am I going to do for the rest of today and on Thursday and on Saturday? Okay, so first I have to explain the ingredients of ADS-CFT. And I'm going to choose 2 of them. Okay, obviously an important ingredient seems to be supersymmetry. But this is a huge topic by itself, so I decided not to talk too much about supersymmetry. And if you know what it is, then you'll be pleased to know that it's very important in this context. But if you don't know what it is, you can also understand the rest of the lectures without me explaining it now. So first I have to explain what is a conformal field theory in 4 dimensions. And then I have to explain the geometry of this anti-de Sitter space. Okay, so these are the 2 most important ingredients which I chose to explain to you, and this will take us the remaining of today's lecture to understand what these 2 things are. And then in the second lecture on Thursday, I'm going to explain the ADS-CFT correspondence and its origin from superstring theory well, explain will be a big word because, of course, superstring theory, to explain really superstring string theory, that would take me a course of about 3 months. But at least I'll do what I can do in 90 minutes to explain what this is about. And then in the third lecture on Saturday, we will introduce some generalizations. So I mentioned to you that apart from being conceptually very exciting, this correspondence is actually very useful because you can map strongly coupled quantum field theories to classical gravity theories. And of course, you can imagine that this has lots of applications whenever you can't calculate something in a strongly coupled quantum field theory. And I want to show you some applications where you can actually see what can be achieved. And that will happen on Saturday. So introduce. So there will also be some relation with the black hole course, which we have during this week as well, since in particular I'm going to talk about finite temperature, quantum field theory, and I'll show you some potential applications to real-world physics. Okay, so maybe this also gives you a flavor of what is the excitement about the subject. So one, you have this conceptual problem of mapping something quantum to something which is gravitational, but also it's a very nice example where you can take something, a concept from string theory, and really calculate something for the real world. Okay, I mean, in a particular sense, which I'm going to explain on Saturday. Yes? Yes.
This corresponds to the real duality. So you tell us that it maps quasi-classical limit of gravity to the strong limit of the quantum field theory. And what about the quasi-classical limit of the quantum field theory and some really quantum limit of the gravity?
Yes, a very good question. So the conjecture is also that the correspondence works also the other way around. But unfortunately, it's very hard to test it the other way around, because then you would have to have a strongly coupled string theory on a curved space. And that's not a well-defined concept so far. So you can't do any explicit calculation. Yes, in principle you can, but unfortunately we know so little about strongly coupled quantum field theories that we don't know, we can't understand. I mean, you're totally right. So in principle, if I take a perturbative quantum field theory, this should give me some predictions about strongly coupled quantum field theory. But unfortunately, we know so little about strongly coupled string theory on curved space, sorry. But we know so little about this that we can't interpret the prediction. So that's a shame, but hopefully, when you finish your PhD, we can also do that. And the
second question about this space of states in the string theory, which is, as you said, equal to the space of states to the quantum field. We talk about the whole space of states of the string theory, or about space of states of the one string.
No, of the whole theory. I think I will go into more details in the course, and I think this points also already to things I'm going to do on Thursday, because I really want to understand how you can map. I bear this question in mind. It's a good question. I think I'll address this on Thursday. Good. Okay. So thanks for the nice questions. So I kind of introduced what we're going to do. And now I'm going to be a lot more technical, because hopefully I'm going to introduce this and that concept now for the rest of the lecture. Also, because the examples this afternoon, they will be about conformal field theories in 4 dimensions and about the geometry of anti-de Sitter spaces. So that's relevant for the classes this afternoon. One other remark about, so when we hand out the examples sheet outside after this class, we hand out all the examples for today and Thursday at once. So there are 12 examples. But we are well aware that we can't do 12 examples in 45 minutes. So today you should first read the first 6 questions, because they will be about anti-de Sitter spaces and about conformal field theories in 4 dimensions. Okay, so just read the first 6, and the other one are for Thursday. And also the questions will be in increasing order of difficulty. So you shouldn't do all the 6 questions. But the first ones will be more easy, and the third one will be more complicated. The same, the fourth will again be easy, and the 6th one will be more complicated. So that's how these are organized. Okay, so now let me go into more detail and explain to you what a conformal field theory is in 4 dimensions. I guess I'm supposed to use this to clean the board. Let's just see. Does anybody have a handkerchief or something? Fucking paper. Thanks. Sorry about that. Thank you very much. Okay, so let me talk about conformal field theories in 4 dimensions. Let me start in d dimensions and then we'll restrict to 4. So, and the first point is to look at conformal coordinate transformations. So what's conformal symmetry? So these leave angles invariant. So this is meant locally, so at every point in space. And so this means that instead of having a tensorial coordinate transformation, the line element is going to just change with a scalar function, which I call omega to the -2, for some reason which will be obvious in a second. And so then I transform to some new set of coordinates x primed in such a way. And let me say that for the purpose of explaining conformal transformations, I'm going to consider a Euclidean space, because that's what's usually done in this context. But let me point out already here that ADS-CFT works as well in Euclidean as in Minkowski space, and later we'll also switch to Minkowski space. So here we consider so we start in d dimension, but soon d will be 4. Okay, so now we can change to an infinitesimal transformation. And then we have x prime being the old coordinates plus just some infinitesimal vector v mu. And if we do that, we will write our omega with a function sigma in such a way. And in fact, it will turn out that this sigma will be the divergence of this vector v. Okay, so this means the divergence of this vector. And if we take this infinitesimal ansatz and we plug it in this original equation, then we get the so-called conformal killing equation. So then we obtain the conformal and this reads like this: d mu v nu plus d nu v mu is equal to 2 sigma times the metric on flat space. And because here we're in Euclidean space, our metric is just delta mu. Okay, and what's interesting to note is that you can, so this I derived just in flat space, but the left-hand side of this equation is actually the flat space restriction of the diffeomorphism of a metric in a curved space. So this is just a technical side remark for which might be interesting for some of the more complicated examples. So note d mu v nu plus d nu v mu is the flat space restriction of a diffeomorphism. I'm going to write down what it is in a second. Of a metric of a curved space, And so where we have that this metric in curved space transforms with the Lie derivative along this vector, and this is just the covariant derivative acting on u minus. Okay. Anyway, that's just a side remark, but now we want to solve this equation here, this conformal killing equation. And I'm going to write down the possible solutions of this equation. Right, so obviously if this is a constant, then this equation will be satisfied. So the lowest order solution is just a constant vector. Then this equation also admits rotations given by an antisymmetric matrix omega mu nu. And then we can have dilations or scale transformations which look like this. And the highest you can possibly have is the so-called special conformal transformation, which looks like this. Okay, so this is our most general solution. So here you see we have something which is quadratic in x. Here these two terms, they are linear, and this one is a constant. So this is translation, rotation, scale transformation, and this one here is called special conformal transformation. Okay, so omega is an antisymmetric matrix which generates rotations, and this function sigma, here if we insert v into here, then we obtain that this has a constant contribution from the scale transformation and something which is linear from the special conformal transformations. Okay, and that's true in any dimension, which can in particular be bigger than 2. And these transformations form a group. And here in this Euclidean signature, this group is called SO d plus 1, 1. And in Minkowski space, the group would become SO d, 2. Okay. Okay, so now I come back to your question about what happens in 2 dimensions and what happens in 4 dimensions. So now if you would go to a course on conformal field theory, then at this point of the lecture, the lecturer would probably say, okay, now let's go to 2 dimensions, because there this group is special and it has many more symmetries than the ones I've written down so far. But that's what we don't want to do here, because here we want to talk about 4 dimensions. So maybe you can answer the question, if I go to 2 dimensions, what happens with the conformal killing equation while I clean the board? Okay, if you see this equation d mu v nu plus d nu v mu is equal to 2 sigma eta mu nu. So now if you go to 2 dimensions, something special happens. Do you remember? I'll tell you in a minute. When I finish cleaning the board, I'll tell you. So while I'm cleaning the board, everybody can think about this question. So what happens if you do this in 2 dimensions? Yes, why? Yeah, the set of solutions becomes infinite dimensional, that's correct, but why? What is special?
In 2 dimensions, the fundamental group of SO2 is infinite.
Yes, okay, I wanted to phrase it in slightly more physical terms, but you're absolutely right. Okay, so, well, if you're in 2 dimensions, then you only have 2 coordinates, and then these equations become really simple, and in particular, they become the Cauchy-Riemann differential equations. Okay, and then it just means that any holomorphic function will be a solution, and then you have an infinite number of solutions to these equations. However, unfortunately, in this lecture, we're not going to go to 2 dimensions. So we won't get the Cauchy-Riemann differential equations, and this means we won't have an infinite number of conserved quantities. And that's the difference. So in 2 dimensions, conformal symmetry is extremely powerful symmetry, but in 4 dimensions, it's still quite nice, as you'll see, but it's still a finite group. Okay. So let me just quickly write this down. So in 2 dimensions, the conformal killing equation reduces to the Cauchy-Riemann equations. Well, okay, I can look at the different components and insert them into the conformal killing equation, and then so I just have d1 v1 is equal to d2 v2, and d1 v2 is equal to minus d2 v1. And as you already pointed out, this means I have infinitely many solutions. And according to Noether's theorem, if I have infinitely many solutions, then I will have infinitely many conserved quantities. And then I have a so-called integrable theory. Okay. But however, in this lecture, we will stay with d bigger than 2, because in the end, what we want to do, we want to describe theories relevant for instance, elementary particles in the real world, and so our real world somehow is 3+1 dimensional. So, and that's the reason why we consider this as higher dimensional case. I should say, also for d equals to 2, there are very powerful versions of the ADS-CFT correspondence. They won't be the topic of this class here this week. And then the conformal group remains finite. Okay, and you can count how many independent conserved quantities there will be. And this you can discuss also this afternoon in the examples classes. Just count how many independent parameters there are in A, mu, omega, lambda, and B. And so here we stay in dx to 4, and sometimes at the end I'm also going to mention dx to 3, and that's due because we want to look at physical applications. Okay. Okay, so now what's a conformal field theory? So we have this conformal symmetry, and a conformal field theory means that the fields have to transform covariantly under these transformations. So conformal field theory means the fields transform covariantly under conformal transformations. And so let's consider a particular conformally covariant operator, which I call O. And so in a CFT, a conformally covariant operator, which I call curly O, which is a so-called, so the mathematical word is a quasi-primary operator. Transforms as follows. So you can write an infinitesimal transformation with, as parameter again, this vector v, and you make it act on your operator O, and I tell you that the transformation is given by an operation LV, which I'm going to write down in a minute. And this LV is given by the product of this vector v with the derivative, higher dimension derivative. Then there's a term which involves this function sigma with the parameter delta, and this is the so-called scale dimension of this operator O. So every O has a scale dimension delta. And then there's also a term which involves the spin part. So assume that this operator is a vector or a spinner or something, then I also have a contribution which acts on these indices, and I'm just going to write them here for completeness, but we're not going to need them for the examples this afternoon. And there we have an antisymmetrization. So these brackets mean that we antisymmetrize these indices. And then we have a group generator here, and that's a generator of the group OD. Okay, that's just for completeness. If we have scalar operators, we only have to worry about the first two terms. And so in particular, scalars, we have so if I have a scalar field phi and I apply this transformation, then the spin component goes away, and I just have minus v dot del plus delta times sigma of x into phi of x. And this you're going to need to do some of the examples this afternoon. Okay, and so if we have fields with, so these conformal field theories are very special because the correlation functions will be very simple. They will be really extremely simple, and I'll show you how they will look like. Oops. Mm-hmm. Delta is the conformal dimension, and sigma of x is this function sigma which we defined above. Okay? Mm-hmm. Yes.
It's a result of the diffeomorphism of the method?
Yes.
It's a constraint?
Well, okay. Okay, there's another question which we consider in the examples class this afternoon. So here I showed you the left-hand side you get from the diffeomorphism. But the right-hand side will come from a so-called Weyl transformation of the metric. If you combine the Weyl transformation and this diffeomorphism, you get the conformal killing equation. Good question will be discussed this afternoon in the examples.
This equation is the result of the symmetry
of the metric, yeah. So if you have a Weyl invariant metric, then you get a conformal field theory in flat space. Yes, good question. Anything else? Good. Yeah. Yes, the conformal killing vector. V is called the conformal killing vector, yes. Okay, so let me just briefly, so you see that it's a very, even if it's finite dimensional, because we are in more than 2 dimensions, the symmetry is still very powerful, and it constrains the correlators to be of a very simple form. Okay, so let's just say a few words about conformal correlation function. So usually, in any quantum field theory, not only the conformal ones, if we have a correlation function of 2 operators, it's usually written in this form, but really what this means is that you consider the so-called time-ordered product. But this is not really relevant here. Here, the relevant statement is that since we have such a high degree of symmetry, these objects will look very simple, even if your theory is complicated, as long as it's conformally invariant. And so normally, if you calculate such an object, you have to do Feynman diagrams, and this can be quite complicated. But here it's easier. So in a conformal field theory, the symmetry is so strong that it determines the form at least of the 2 and 3 point correlation functions up to a small number of parameters. And I'll give you just quickly 2 examples, and this will be discussed more in the examples classes this afternoon. And unfortunately, I have to rush a little bit because I also still want to tell you about the anti-de Sitter spaces before we finish in about half an hour, because you also need them for the examples this afternoon. Okay, so the simplest example is to have just a scalar 2-point function. And as you will calculate this afternoon, this is just determined by one constant, and in configuration space, in position space, so if this is a field of dimension delta, the correlation function is going to have this simple form. It will be non-zero only if the scaling dimension of these 2 fields is the same, otherwise it's 0. But this C here is the only coefficient which is not determined by the conformal symmetry. It will be determined by further ingredients of the theory. So if to determine what the C is, you will have to know the explicit Lagrangian of the theory. If you just know my theory is conformal, you know the space-time dependence of the correlator is just going to be of this simple form. But if you want to know what the C is, you have to need the Lagrangian in addition. So this is determined by the field content of the theory. Okay. And just as a final step, let me write down what the 3-point function looks like if you have 3 different scalar fields in a conformal field theory. And again, it's determined up to one scale, which is not determined by the conformal symmetry. So again, for this k, you have to know what the Lagrange looks like. And then, but the functional dependence on the space-time variables is fixed by the conformal symmetry. So you have one field of dimension delta 1, one field of dimension delta 2, and one field of dimension delta 3. And then you have the structure here. Then you have y minus z to the delta 2 plus delta 3 minus delta 1, and z minus x to the delta 1 plus delta 3 minus delta 2. Okay, so the 4-pointer in higher functions, they will look a little more complicated than these simple examples, but even in higher dimensions, the 2- and 3-point functions, they will have this rather simple form. Mm-hmm. Yeah, well, okay, here, this is just the example of a scalar. You can also write down conformal correlators for spinors, vectors, tensors, whatever you like, but they look a little more complicated. So here I just give you the simplest example, but I gave you this. So if this thing comes into the game, it's going to look a little more complicated. So if you want to know, when I did my PhD, I looked at the conformal 3-point function for 3 energy momentum tensors. And there you have 3 independent forms. But okay, this took me a while to figure this out. Okay, it becomes a little more complicated, but not, well, it's still manageable. But here, just for brevity, I just mentioned the scalar case. Mm-hmm. Oh, okay, very good question. Okay, so in a conformal theory, you don't really have an in and an out state because it's conformal symmetry. You can't really define an S matrix. So here, what you do is you define it as a time-ordered product, and then just the symmetry tells you what you can have for these functions. But okay, there's no relation to an S matrix here. That's probably important to know. Yeah. Yes, exactly. Yeah. Yes, okay, here I'm just in the Euclidean space. Okay, but it's a very good question, and on Saturday I'm going to talk about retardant advanced green function, but then we have to go to Minkowski space. And also next week there will be a lecture by Damson, and he's going to discuss Minkowski space, and he will be very careful about defining retardant advanced propagators. So we can also deal with retardant advance in the context of ADS-CFT, but here, just for simplicity, I just work in the Euclidean. Okay. Mm-hmm. Oh, sorry. Okay, yes, this is a sloppy notation. So if I write this, okay, very good question. Okay, so this is a shorthand notation of a physicist. But really what this means is that I take a scalar product, okay? Or if you want, you can put indices. So up and down doesn't make any difference because it's Euclidean. Okay, so really if I write this, I mean, okay, I take this whole thing and then I take it to the power delta. Okay, sorry, I should have mentioned this. Okay, so you take a scalar product and then you take it to the power delta. Okay, thanks for asking lots of questions. I think you can go on in the examples classes, but I think I do have to tell you a little bit about anti-de Sitter spaces now. Okay, so this conformal symmetry is certainly one ingredient on the field theory side. So now I've been talking about the field theory side of the ADS-CFT correspondence. And so we have these conformal field theories. But now I want to tell you a little bit about the anti-de Sitter spaces which show up on the other side of the correspondence when you talk about gravity theories. Okay, so, and of course this is also a very important ingredient for understanding ADS-CFT. So this is the next chapter. And okay, so let me give you a definition of anti-de Sitter space, and then I'll show you how to write the metric in various coordinate systems which are useful. And so the most important thing to know is that it's a hyperbolic space. And as we also note, it's a space which has a boundary. Okay. So let's write the p plus 2 dimensional anti-de Sitter space, which I abbreviate with ADS p plus 2, is represented by a hyperboloid and it satisfies the following equation. So we have coordinates capital X, and the 0th one of them and the p plus 2nd of them, they appear with a plus sign here in this equation, and all the others, they appear with a minus sign. So if you had a sphere, then all the signs would be pluses, but since here we have a hyperboloid, here the sign will be turned around. And so this will be equal to a constant, and this constant called L will be the so-called anti-de Sitter radius. Okay, so again, compared to a sphere, so in a sphere this minus sign would be a plus sign. Okay, and this equation I'm going to call star. And so this, I have embedded this hyperboloid now in p plus 3 dimensional space by this equation. Okay, and so we can write down a metric. ds squared is equal to minus dx0 squared minus dx p plus 2 squared, and then plus I is equal from 1, goes from 1 to p plus 1 dxi squared. And so by construction, the space has an isometry. Which is SO2, p plus 1. Okay, so it just means 2 of the coordinates have another sign here as the other ones. Okay, also it's a homogeneous and isotropic space. Yeah? I think, yes, you're right. What do you think? Yeah, I think I'm doing Euclidean. Yes, you're right. Okay, but now we want to solve this equation. And for this purpose, we introduce a new set of coordinates. So this equation star is solved by a new system of coordinates, which we call, so we introduce new coordinates in this way. So this x0 gets replaced by the hyperbolic cosine of a new variable rho times the cosine of a new variable tau. And x2, xp plus 2, I'm going to replace, again, this ADS radius comes there for dimensional reasons, and then I will have the hyperbolic cosine of rho times the sine of tau. And the xi coordinates, they will be replaced by the sine hyperbolic of rho times angular variables omega I, where now I goes from 1 to p plus 1. And so if I sum over the squares of these omegas, I get 1. Okay, and so if I do this replacement, I'm sorry I couldn't clean the board any better than that. I hope you can still read it. So then I get a new metric which looks like this. ts squared is equal to L squared into minus cosh squared rho d tau squared plus d rho squared and then plus sinh squared rho d omega squared. Okay, so this describes a hyperboloid, and there are some restrictions on these coordinates. So in particular, the coordinate rho has to be positive. And also, so this variable tau will be periodic. And it goes from 0 to 2 pi. And this covers the entire hyperboloid once. And that's why these coordinates are called the so-called, so this means that tau, rho, and these omega I are the so-called global coordinates. Okay, so now we see actually, so tau is the variable which corresponds to time, and in this way we actually have closed time-like curves because tau wraps around this hyperboloid. And well, that's fine, but if we want to have a causal space-time and some causal structure, we should better change to another picture where we unwrap this coordinate here and get a causal structure where time goes from minus infinity to infinity. Okay. So, so this coordinate tau wraps S1. And so to obtain a causal spacetime, you should unwrap this S1, which means take that tau goes from minus infinity to infinity without any identifications. And if we do that, we get the so-called universal covering of the hyperboloid. Okay, I'm going to draw a picture in a minute. Okay, so we should really introduce another coordinate to achieve this unwrapping, and I'm going to show to you how this works now. Okay. Okay, so in the end, what I'm going to show to you is that we get a space, this anti-de Sitter space will be a space with a boundary. And then this means, and actually this boundary will be equivalent to a flat space. So this means if we take, for instance, a 5-dimensional anti-de Sitter space, it's going to have a 4-dimensional boundary. And then we can view our quantum field theory, which enters the ADS CFT correspondence, as being defined on this flat space, which is actually at the boundary of the ADS space. So that's where we're heading towards. And so let me show you how we get this causal structure. So for that purpose, it's convenient to introduce a new coordinate. Which is going to be called theta. And this will be related to the coordinate rho, which we had up there, by tan theta is equal to sine hyperbolic of rho. Since the condition on rho up there, we actually find that this implies that theta will be limited to lie between 0 and pi half. And so if I do this transformation, then I get a new metric ds squared, which is L squared over cos squared theta, and then we have minus d tor squared plus d theta squared plus sine squared theta d omega squared. Okay, so if I don't put any indices on the omegas, it just means I just pick one, and then we have an ADS3 space. Okay, and now we can do a conformal rescaling, which means that we remove this factor here at the front, and so we get the following, a new metric, which doesn't have this factor at the front, and this is going to be minus d tor squared plus d theta squared plus sine squared theta d omega squared. Okay, and since now this variable theta is restricted to only go to the pi half, we actually discover it's just, we just cover the half of a hemisphere if we do that. And so now finally I can draw you a picture of my ADS3 space where I just pick one of these omegas. And it's going to look like this. So it looks like a cylinder, so we start with a plane. Okay, so, and then, so this is my cylinder. And okay, so this is just a cut through the cylinder. And okay, the angular variable here is going to be the omega. the variable in this direction is going to be the tau. And so now this space here is actually curved, and it covers the upper half of a sphere. Okay, so this, okay, I have this surface here corresponds to the upper hemisphere of a sphere. And so this means if I'm at the north pole here, this is where theta is equal to 0. And if I'm at the equator, this means that theta is equal to pi half. Okay, and we see that our space has a boundary. Okay, the boundary is just here the equator, and then of course it goes along the cylinder as well. Okay. So if we look at the metric here and this figure, then we actually see that this is the metric of 1/2 of the so-called Einstein static universe, which is just the space R times SP. And okay, so and the fact that we have 1/2 is related to the fact that this theta just goes to pi half. Okay. Okay, and as I said, this equator is a boundary of the space. So the equator at theta is equal to pi half is a boundary of the space. And of course, the boundary also extends in the tau direction. And so the topology of this boundary is just SP. So let me add to the sentence with topology. So we are definitely in the Euclidean alias here. And now this is actually equivalent to the conformal compactification just of a flat space. So we can say the boundary of our anti-de Sitter space is conformally equivalent to a flat space. So that's an important sentence. ADS P plus 2 is identical to the conformal compactification of flat space. Okay, so, and that's pretty crucial for the whole ADS-CFT correspondence. I mean, okay, it's a geometrical fact so far, but this will be really, really important. Okay, so maybe you wonder about this word conformally compactified. Okay, so basically a conformal transformation in this curved space environment means that I change the metric here by a prefactor. If you remember our definition of conformal transformations is if I just have a function of the variables at the front, I can just rescale by multiplying by its inverse and then it goes away. So that's a conformal transformation, okay? Okay, and so what we have learned ADS is a space with a boundary, and the boundary is equivalent to a flat space. Mm-hmm. Yes, that's right, yes. And now for ADS3, I just took one variable. Yes.
So together with theta in the A plus plus.
Yeah. Okay, did I miscount the piece? Okay, I will have to look at it again. You're probably right, but if I start counting the piece here, I'm going to confuse myself. Yeah. Okay, that's a very good question. And I think in the examples classes, there will be many more chances to talk about ADS spaces. And okay, we're almost done, and I just, such that you can do the examples well, let me just mention 2 other facts, and then you can all go for lunch, and I can also go for lunch. Okay, so, oh God. So the last thing I want to mention is that there's yet another system of coordinates which are very useful for ADS spaces, which are the so-called Poincaré coordinates. And let me just define them for you. And then we are done for now. Okay, so another set of useful coordinates are the so-called Poincaré coordinates. And they defined as follows. So we have, for this x0, we write 1 over 2y times 1 plus y squared, L squared plus L is this anti-de Sitter radius again, minus t squared, and xi is going to be L times y times small xi, where I runs from 1 to p, and then I have xp plus 1, which is 1 over 2y times 1 minus y squared, L squared minus x squared plus t squared, and xp plus 2 is going to be L times y times t. And then I have a new set of coordinates, which is y, t, and x, and which has the properties that y is positive and x is an element of Rp. And then I get ds squared is L squared over dy squared divided by y squared plus y squared into minus dt squared plus dx squared. Okay, and this is called the Poincaré coordinates. And so here the boundary is when y goes to infinity, I think. Okay, I should check that. Okay, so so the important point is that they cover only half of this hyperboloid, which we're considering at the beginning. Okay, but for practical purposes, this set of coordinates will turn out to be extremely useful. And so the last thing I want to say before you are really relieved is about the curvature. So this ADS space has a constant negative curvature because it's a hyperboloid. And this means that the Riemann tensor looks like this, minus 1 over L squared into G mu rho minus G mu rho G nu sigma. Oops, did I get these right? Mu. No, okay, this should be a sigma. So I think then it's correct. Okay, so the Riemann tensor has this really simple form. It's a so-called Einstein space, and the curvature is negative. And so that's also a very important feature which we are going to use. Okay, I'm sorry for keeping you for so long, but I think these concepts are all really useful and important for the ADS-CFT correspondence. And also I wanted to show them to you such that you can do the examples. And so I should point again out that you shouldn't forget to collect your example sheet. Okay, somehow I always pushed on the... Oh God. Okay, on the top board it says, don't forget to pick up example sheet outside before you leave for lunch. And okay, so thanks a lot and have fun this afternoon. I see you on Thursday morning.